Good to go. Well, welcome everyone. Thanks for joining. Arxiv Dives with Oxen.ai are deep dives into archive papers. The main motivation is just to make us smarter every week. I think that diving into these archive papers is one of the best ways to learn the fundamentals while keeping up. While keeping up with the bleeding edge of AI research. So I feel like there's a lot of noise out there sometimes, and just like coming back to the actual research papers and diving into them is the best way to really understand deeply the fundamentals. So today we're going to be going over the LoRA paper by the team at Microsoft, and I'll be publishing all these notes that we are following along with on our blog. And Scott, if you could put the link to the Notion doc, if you guys want to scroll along live with me, we'll have that in the chat there. So with that being said, I will pull up my notes, and I will also pull up the paper here and put it in the chat. So if you want to like have the actual paper next to you, that can be helpful as well. Here's the paper here. All right, so this paper came out in October of 2021 from team at Microsoft and some researchers at Carnegie Mellon. I'm going to go over just like a little background knowledge before we hop in to the actual paper itself. This one's one of the more math heavy papers that we've done so far. So I'm going to try to break down the concepts. They're pretty basic linear algebra concepts. And if you kind of know how to add and multiply numbers, you hopefully should be able to follow along with everything. And while I'm starting with the math and why, and we'll dive into the paper and how they apply these things to transformer models such as GPT-2 and GPT-3. So at a high level, LoRA reduces the number of trainable parameters in a model, which results in a decrease of training time and GPU memory usage while maintaining the quality of the outputs, is what they claim. And how it works is traditionally in a neural network, you'll have a large set of weights. If you're familiar with Paris, you can print out like how many parameters are in each layer. You might have some dense layers that are just giant matrices that you're multiplying together. And what LoRA does is on the side, it has two other matrices, they call them A and B, that are sitting next to your pre-trained weights within the neural network. And we're actually just keeping the pre-trained weights frozen and updating these rank decomposition matrices is what they call them on the side. So it's helpful, I think, to go back to the basics of linear algebra. And if you have two matrices and they both have different dimensions, these are very small ones, but a 3x2 and a 2x3, if the middle number matches between those, then you can multiply them together, and the resulting matrix is the numbers on the outside. So in this case, they have pre-trained weights, which are D by D. And as you roll through a linear layer, it's kind of that standard y equals wx plus b computation. So what they do, and I think it might be helpful to have like a actual dense layer in mind, like these 512 by 512 as we're doing it. So you can imagine a 512 by 512 matrix is about 200,000 parameters. Now, what they're going to do is they are assuming that a lot of these values in the matrix are not independent of each other, and that the matrix has some sort of rank that we can decompose the matrix down into. So they choose a number that's way smaller than the 512 by 512. In the paper, they go all the way down to 1 or 4. And what they do is they make two matrices on the side. So if we're using our 512 example and a rank of 4, you could have an A matrix that is 512 by 4, and then a B matrix that's 4 by 512. And that's only 2,000 trainable parameters instead of 20,000. So if you look at our initial equation, it's y equals wx plus b. They just modify it to y equals wx plus b plus b times a times x. So with our actual values there, if you have an input to the network that's like 512 by 1 in terms of an x, then you would have y equals 512 by 512, which is this w here, times the x, which is 512 by 1, plus b, which is also 512 by 1. And then it's 512 by 4 times 4 by 512 times 512 by 1. And so our total number of trainable parameters goes from 200,000 to just this A and this B matrix, which is 4,000. So while training a neural network, there's a lot of places that you can optimize that are useful to keep in mind. And one is, what is the total model size? So this might be like your size on disk, which also pertains to like size over the network if you tried to download your model and run it. There's the size in RAM, there's the size that goes into the GPU, and there's the size that you might be running on CPU. So that's like the total model size. There's also the inference size. So how much of this do you need to be able to load into your GPU? And depending on how many examples you're throwing through at once, depending on your sequence length, and depending on the data size as well, that could be the model size times whatever your batch size and sequence length is. And then there's the memory needed for training, which is all of the model parameters plus all of the gradients while you're training your model. So if you're familiar with backpropagation, this is a very small neural network, but you can see there's like all the weights that are propagating forward and the values that are propagating forward. But during training, you also need to keep track of all the values that you're updating as you go backwards. So if you had a model that was like 2 gigabytes for the forward pass, just like rough estimation, you might need 4 gigabytes to do the full training. And when we get into models that are the size of like GPT-3, where they have 175 billion parameters, that means you need like 350 gigabytes for the forward pass, and then like almost a terabyte of data for the backward pass. So that is just an insane amount of memory to have. And so that's one of the main motivations behind having these side layers that LoRA can optimize, is we're just training this much smaller set of weights on the side, and we're not training the entire neural network. I think another interesting thing about LoRA is not only does it reduce the total memory needed for training, but it also doesn't doesn't affect the forward pass at all, because you can take, again, that initial equation for LoRA, which is like Wx plus B plus Bx BA times X. You can rewrite that as putting these guys right next to each other because it's just addition. And then you can rewrite it again as factoring out the X in both of those, and then you're just adding W plus BA. And once you add W and BA, you get a new set of weights, call that W1. And now Y is just back to Y equals W1 times X plus B, which is the same amount of compute that you did at the beginning. It's just a slightly new set of weights. And we'll see how they use that in the paper to like you could have 100 different fine tunings on the same base model. And instead of duplicating all the weights from the base model over and over and over again, which in like a GPT-3 scenario, you might have 350 gigabytes of weights, and fine tuning that whole thing and saving it off means you're going to have another 350. In this case, they have like 35 megabyte fine tuning LoRa's that are sitting out there. So you could have hundreds of those and just one of your big base model. And it's way more efficient to just add in these weights when you're ready to do inference, and you have no more inference time, and you can just store a lot more of the fine tunings. So that's some background. I'll pause for any questions so far before we get into the actual paper details.
So, sorry. Oh, go ahead, Jonathan.
Yeah, real quick question. So I guess I had a misunderstanding. They're not actually subsampling the parameters, but they're actually adding more parameters, but in these sort of independent matrices. Is that right? Or
yeah, so they have the independent matrices sitting next to the actual weights of the neural network, and then when they go for inference time, they add those together, and you can either run them next to each other like this, or you can merge them into one layer just by having the addition in there. Does that make sense?
Yeah, totally. Thanks.
And did you have a question?
Yeah, potentially naive question. But I was thinking about what you were saying in terms of being able to have multiple different fine-tuned variations of a base model without having to duplicate the majority of the parameters each time. Is this a much more like performance way to do that than just, having a couple of layers at the end change and kind of bolting those onto an existing base model? Or is it just more storage efficient, or like what's the advantage here?
Yeah, totally. They dive into this a little bit later. They call what you're talking about adapter layers, where you might like add another layer in the middle and just train that, or add another layer at the end. And they're claiming that one, adding that layer does add a little bit more compute to the total inference time, even if it is a small layer. And then you also have to run that sequentially. If you're doing layer X, then layer Y, then layer Z, you have to do them in that order. And so the ability to merge all of these weights into the initial weights through an addition means you can still take advantage of the GPU and the parallelization of the GPU while not running each of the layers sequentially.
Very cool.
Good questions. So that was kind of just a little background, and I honestly had to look up a lot of the math after I read the paper so that the paper made more sense. So I thought it'd be nice to just start with that.
You did a great job in the explanation. Kudos.
Thank you. So the current paradigm of training natural language processing models is pre-training on a large corpus of general data, then fine-tuning to specific task or tasks. Like we said, with large models, full fine-tuning of all the parameters becomes prohibitively expensive. I talked about GPT-3 as an example and how you have to store all of those gradients, and let alone if you want to store multiple fine-tuned models, you have to set up, save off all of the parameters multiple times. They claim that LoRA can reduce the number of trainable parameters by 10,000x, which is an extreme example, and that's with the GPT-3 and a rank of 4. So you can imagine, like, since GPT-3 is already so big, those matrices in the middle are much larger. But if you did this for like a GPT-2, where the inner matrices are smaller, you don't get 10,000x for every type of model. That's just kind of at the extreme. And so yeah, in reality, it really depends on your model size. And I found a nice tutorial where they were doing this with GPT-2, which is obviously much smaller than GPT-3. It's just that the Keras examples here. And you can see a GPT-2 normally takes about 4 gigabytes of GPU memory to do the full training. And a LoRA training cuts that down to like 2.5 gigabytes. So again, the 1000x is pretty extreme, but it honestly does give you a good bump. And I've done it locally with Llama 2, which would be another example here. And Llama 2 like has a 7 billion parameter model, which if you kind of double the parameters, that's how much you need to fit on the GPU if you did like floating point 16. So 7 times 2 is 14. That means I need 14 gigabytes of RAM to run Llama 2 7 billion forward. And if I wanted to do a full fine tuning of that and do the backwards pass, that means I need a GPU with like 30 some gigabytes of RAM, which I don't have. But LoRA reduces the number of parameters I need there. So I can actually run, I can fine tune a model that needs 14 gigabytes of RAM just for the forward pass with 16 gigabytes for the full backwards pass, just because I'm only optimizing the LoRA weights. So I found it super useful in the Llama 2 case where I just don't have a GPU that can do the full fine tuning. And then they say LoRA performs on par or better than fine tuning despite having higher training throughput and no additional inference latency.
One thing that they didn't mention that I thought might be interesting is like I know like most other fine-tuning approaches tend to have like unintended consequences on other tasks, and I'm curious if like LoRA like mitigates that risk at all, right? Where like if you train for task A, sometimes you inadvertently hurt your performance on task C. I wonder if LoRA did they mention anything about that?
They didn't, but I saw in like some other posts when I was researching it, some people talking about that, and they were talking about how fine-tuning data sets are often much smaller than the pre-training data sets. And since LoRA relies on updating a much smaller set of weights, this is advantageous when you have a smaller data set to fine-tune on, because now you're not like overfitting to that smaller data set and you're just updating the smaller set of parameters. Was that your intuition too?
Yeah, that was my intuition. And it also just makes like the experimentation costs lower to where you're like, if you're trying to do full fine tuning and you kind of get it wrong, right? Train too long, don't train enough. It's like, oh, you wasted a lot of compute cycles. But if you can do this, then you can potentially like just try different things easier.
Yeah, totally. In the introduction, they just talk about in general how language is one of those tasks where you can have a general model that can complete a lot of English sentences with like the most common next words, but the problem with human language is there's many valid continuations for the same sentence. So I made a funny little meme here, but like the classic, oh, we know each other so well, we always finish each other's, and then one person says sandwiches and one person says sentences. Like, you can't have one model that always does it all. And they give more concrete examples of like summarization in your own voice or natural language to SQL queries. You might have like one variation of SQL that has one syntax and one variation of SQL that has another syntax. And it's hard to necessarily just construct a prompt that can show you all the variations in syntax you want. It's much easier and more robust to have a full fine-tuning data set that can like have all of that data. So I like to think about how many different opinions people have on different topics based on their past experiences. And so fine-tuning, I feel like, is just ways that you can take that general model and make it more robust in those other scenarios. So I talked about the natural language to SQL, the summarizing text in your own voice. We talked about the downsides of fine-tuning end-to-end means you're linearly increasing the storage and memory of each new model. Then this was to your point, like people have solved this problem by just adding external layers and freezing layers below, or maybe freezing these layers and just fine-tuning this layer. They feel like, one, adding the layers at the end, like I said, makes just another step in the process. And then two, being able to apply these LoRA layers to anywhere within the model has its advantages as well. So that's just that tutorial. They lean into the fact that these large language models are over-parameterized. And so they hypothesize that there is a low intrinsic rank of the matrix. And I think it's helpful to think about what rank is in the concept of linear algebra. It's the number of linearly independent rows and columns. So if we just like had a small, or if we had a matrix of all zeros, the rank would be 0. If we had a matrix that kind of looked like this, where you have like 1, 2, 3, 4, and 2, 4, 6, 8, these two rows are pretty much just a multiple of each other. So they're actually not adding that much new information, where the third row, I just picked a bunch of random numbers, and that means it's adding a bunch of new information. I've also seen it's really easy for our brains to like understand this in 2 dimensions or 3 dimensions, but these neural networks have hundreds of dimensions. And so you can think of this matrix right here, even though it's 3 by 3, it only has a rank of 2 because all of these points that are sitting out here could be projected onto a plane. So they're all kind of like pointing in the same direction, versus this one, it's a cube. They're all pointing in different directions. And within a neural network, you can just think about that as like each row in the weight matrix is making a slightly different decision about what the neural network should do later. And if it just keeps pointing it in the same direction, then you're not adding new information. So that was kind of their intuition, is these large matrices within like a GPT-3 probably have a lot of rows or columns that are not linearly independent. And so they were testing that out by trying to reduce the rank of those matrices with these side matrices. So LoRA can be applied to any neural network architecture. We've seen it applied to like stable diffusion and other models. In this one, they're specifically doing it for the transformer architecture. And so if you're familiar with the transformer architecture, within there, they have a bunch of weight matrices that are called like the query, the key, the value, and the outputs. And then there's also other modules within there to make a full transformer, but they only apply LoRA, and they do a couple experiments here to the query matrices, the key matrices, and the value matrices. And they say that there is plenty of room for research to adding it to other layers. They were just, it's hard to run every single ablation study possible, and they thought that these matrices would be the best ones to apply it to. When you look in the paper and you see this equation with W0, X, and delta W, that's the same as my Y equals W, X plus B before. They were just using W0 and H as Y. For the B and the A matrices, they use a Gaussian initialization for A, and they use a 0 initialization for B, so that at the beginning of training, A times B is just 0, and then they go from there. And then they mention when deploying into production, you can explicitly compute and store like the new weight matrices as W plus B times A, which we talked about before. And then if you added all of those weights in, you can easily recover the original model by just subtracting BA back out and then adding BA back in with a different fine tuning. So it's kind of a nice, efficient, you could have one model, one big model loaded into memory. And then if a user came in and had a query where you wanted to use a different model, you could just do that quick addition, swap out the fine tuning with very little memory overhead, which is a cool little trick. We talked about how they apply this only to the query key and value matrices, not to the other dense layers. Practical benefits, they did a lot of experiments on some of the BERT models, a GPT-2 model, and then all the way up to a GPT-3 model. That's where I got some of the numbers from before, and I think that that's just kind of insane that GPT-3 needs that much VRAM to train end-to-end. Like, I would love to do the back of the napkin math on how many GPUs you need to run that. So when I was saying the 1000x reduction before, they used a rank of 4, which roughly had the checkpoint sizes of 35 megabytes instead of a full 350 gigabytes. So that's where they got the 10,000x reduction. And like I said, if you stored 100 adapted models, you know, that's only slightly adding versus if you had 100 full trained models, that's like 35 terabytes of data. And then for the GPT-3, they observed a 25% up during training compared to the full fine tuning, because you don't need to calculate the gradients for all of the other parameters. So then they ran a bunch of experiments, like I said, on Roberta, dBERTA, and GPT-2 and GPT-3. They also compared it to a lot of those methods that you were talking about, Ben. So this just looks like a wall of numbers, but LoRA is kind of at the bottom here. And then if you see like adapter D, that's when they did more of the method that you were talking about, Ben, where you add an extra layer at the top or you add adapter layers in between. and they show that LoRA on a lot of these tasks performs better than those adapter layers or full fine-tuning. So that's pretty interesting. They also do it on, so these are all the BERT models. They do it on GPT-2 and compare it to the adapter layers as well. It's interesting because they use a bunch of different data sets when they're fine-tuning Roberta and Deberta, and then they switch to GPT-2 and they switch the evaluation metrics. Not fully sure why they did that. And then they switch the evaluation metrics again when they go to GPT-3. They do wiki-SQL, ML, and a summarization data set. So it's not really apples to apples between GPT-2, GPT-3, and Roberta, but mainly just like taking these models, fine-tuning them. And one of the reasons that they said that they did this was like GPT-3 is so expensive to run that they only wanted to evaluate it on a small set of tasks, and GPT-2 and Roberta are much smaller, so they could do many more iterations on the fine-tuning. But you can even see like the number of total trainable parameters in this model for a full fine-tune versus a LoRA is pretty significant. And the full fine-tuning actually performed slightly worse on wiki-SQL than the LoRA, which feels like just a win-win in that scenario. I was excited to see if they had anything about prompt engineering in there, and they had one paragraph, and they acknowledged that you can use it, but they didn't do any experiments with prompting versus full fine-tuning. I guess because the whole paper is about fine-tuning. Maybe they just didn't want to dive too deep into that. And then they did do a bunch of studies on which weight matrices to apply LoRA to and what rank to use. And so they did it to just the query matrix with rank 4. They did it to just the key matrix with rank 8, etc. Very interesting that the lower ranks consistently outperformed the higher ranks. And it worked the best when you applied it to all of the query key value and output matrices. That was like a interesting fact, like an interesting finding that rank 2 worked the best because that's just less parameters in general. So they took a look at the matrices themselves and did singular value decomposition, which is a more expensive way to find out like which one of these subvectors are linearly independent or not. And you can see the rank of 1, so the lighter these columns are, the more linearly independent they are. Like you can see 1 and 2 have the most independence, and then it just felt like there was a lot of duplication in the other weights as they went down. So they did a few visualizations of what the actual weight matrices look like to validate their hypothesis that, oh, that does make sense that using a smaller number of weights could give you higher performance because it's really just focusing on the weights that are adding new information. So that was pretty much it. Conclusion, future work. Like they said, fine-tuning is very expensive. LoRA reduces the training cost and makes it quick to switch tasks. LoRA is independent of architecture, so they were excited to see what other architectures people apply it to. And it's one of those things, they say it's like orthogonal to all the other techniques, so you can use this in combination. Like you could do an adapter layer and a LoRA if you wanted to. So there's all these types of mixing and matching. that you could do. You mentioned that the mechanism behind it is far from clear, but they feel like the studies of the ranks of the matrices gave them a little more insight than just like a full fine-tuning where you have no insight into why this might have worked better. You could just use a lot of heuristics to pick some of the parameter sizes. But I think, like I said before, it's already helped me do a fine-tuning on Llama without blowing up my hardware requirements. I've seen people adapt it to stable diffusion to, like, for example, if you've ever seen, let me put my face into an image, but obviously it's never been trained on my face. They do the fine-tuning on with LoRA on the side where it learns the qualities of your face and then merges it into the main model. And I feel like we're starting to see a lot of cloud services that are doing this. I know Stability AI was working on a service like this, where they take the base stable diffusion and allow you to deploy a lot of LoRA variations of it. So already seeing it being productionalized now, and I think just in general, it's a pretty cool technique. So that's all I've had. I'm wondering if anybody else has tried it, or like if anybody else is working on fine-tuning models. Any other papers to add on? Just love to open it up to the field now. Or if there's anything confusing during that, because I know it was a lot of math.
I have kind of a orthogonal, I guess, question, but just talking a little bit on what you were saying at the end around how they didn't consider prompt engineering. I guess I've been wondering if you or anyone else on the call has seen any literature kind of like comparing the efficacy of prompt engineering to fine-tuning. Just seems like something that would be kind of slippery to like set up an experiment for. And I'm just wondering if, because I don't know, there's like lots of like LinkedIn posting wars about which one is really going to win or whatever. But I was just curious if anybody had seen that crop up in the literature as well.
Hello.
Yeah.
Well, I personally tried this LoRA in some pages that use stable diffusion like TensorArt. And this LoRA is a lot more restrictive than prompt engineering. For example, with prompt engineering, you actually are telling the model what it should do, but if you put it into production and someone tries to bypass the prompt engineering, it's easy to bypass it. But when you use LoRA, it's like more into the model, and it forces the model to do things that prompt engineering cannot prevent. For example, you can make a LoRA that only use paintings, and all the output of the model will be paintings. And you can try to do the same thing with prompt engineering, but it will not work just as well as with LoRA. I think that's the main difference, that LoRA is like more into the model, while prompt engineering can be easily hacked or bypassed.
Yeah, I definitely, just because of my background, bias towards like data and distribution based solutions like fine tuning, but I just heard you can't deny the ease of like, oh, you can just try a different thing. So good to see that you've seen some tangible benefit from it.
Yeah, it feels like if you're going to productionalize it, and like David said, just like really make sure your model's robust, it does feel like fine-tuning does hone in on your specific task better and make sure that you can't do other tasks. I will say that like the benefit of prompting is if you mess up anything in your fine-tuning, the iteration cycle is much slower. So like it might take 2 hours to fine-tune your model just to find out you didn't add the end character or a new line or something, and then you have to like kick off your fine-tuning again. For prompt engineering, you have a much faster just iteration cycle. So yeah, there's that.
You can actually get your from prompt engineering what you train the model, fine-tune it to. For example, you can make the test with Pro Engineering, and when you're ready, you copy all that examples and do a fine tuning with all their successful examples. It's a way to not do everything with LoRa, but just a mixture of prompt engineering and fine tuning with LoRa. It works a little bit better in time.
Are you saying even collecting data with the prompting and then using the data you collected during the fine tuning?
Yeah, this is mainly what OpenAI fine tuning is up to. When you try to fine tune your ChatGPT model in the interface, I think they use LoRa behind, but you mainly try to give it some prompts, it generates some text, and you use that text to fine tune your models so you can be sure it will do effectively that.
Right, that's clever. It helps with the cold start data problem. Cool. Hey, Jonathan.
Yeah, I'm curious, in the paper, did they mention whether this fine tuning is more effective if you use like a base model as your start model or if you use like a chat model?
They didn't. I think this paper came out. No, it came out after the InstructGPT. I feel like the Llama, you know how they Meta released Llama and then they did the base model and the chat model. I feel like people have probably experimented with that more, but that felt probably too early for this paper. But that's a good question. Have you done any fine tuning, or you just play around with those base ones?
Yeah, I haven't. I'm kind of thinking about doing it, but I'm wondering, like, do you wind up with sort of it's almost like better to deal with like a blanker canvas when you're fine tuning versus one that's kind of already moving in a direction. I don't know whether that intuition applies in this context, but
yeah, I think it would, especially if like depending on your use case, like Meta really fine-tuned the chat model to be helpful and like have a long preamble and really explain things. And if you didn't want any of that preamble and you just wanted to like cut right to an answer, you probably have to unlearn all the stuff that they taught it just to get to yours. So that intuition would make sense to me. Cool. Yeah, we'll turn off the recording now and then just do a more free-form discussion. Thanks for joining, everyone.